Hello everyone. On this video we will be looking at asymptotes of rational functions. Okay, so rational functions are just functions where both the numerator and denominator are polynomial functions. Okay, so starting off we're going to look at the x and y intercepts. Okay, remember to find the y-intercept you make your x equals 0. To find your x-intercept you make your y equals 0 or your f of x equals 0. Alright, so if you are still writing this, feel free to press pause. But we're going to go ahead and move on to our first examples. Okay, so first, I want you to find the y-intercept for f of x equals x minus 3 times x minus 7 divided by x minus 8. And next, I want you to find the x-intercept for f of x equals x minus 12 times x minus 4, that divided by x minus 3 times x plus 1 times x plus 2. Okay, so go ahead and press pause and try this one on your own. Alright, so I'm assuming you have pressed pause and worked this one out, so let's go ahead and verify your answer. Okay, so for your y-intercept, you make x equals 0. So f of 0 is equal to 0 minus 3, 0 minus 7, all over 0 minus 8. So that gives us negative 3 times negative 7 divided by negative 8, which is negative 21 over 8. So your y-intercept is when x equals 0, y equals negative 21 over 8. Okay. Now to find your x-intercept, you make your y or your f of x equals 0. Okay. Now the key to this one is to remember that 0 divided by any non-zero number is equal to 0. Okay. So if you get 0 over 0, that's an indeterminate, and that's a whole different area. But for 0 divided by any non-zero number is going to equal 0. So that means for f of x to equal x minus 12, clean that one up a little bit, times x minus 4 divided by x minus 3 times x plus 1 times x plus 2 to equal 0, we just have to make the numerator 0. Okay, so in other words, x minus 12 times x minus 4 has to equal 0, which means that x minus 12 can equal 0 or x minus 4 can equal 0. Add 12 to both sides, we get x equals 12. Add 4 to both sides here, we get x equals 4. Okay, so those are the two x values that will make our x-intercept. But to find our actual x-intercept, we know that when x is equal to 12, y is equal to 0, or f of x is equal to 0. And when x is equal to 4, your f of x is equal to 0. So these are your x-intercepts. Let me clean that up a little. There we go. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page. And that is finding the vertical asymptote of a rational function. Okay, so for your vertical asymptote, that is really just all of the values of x, or whatever your independent variable is that would make that undefined. Okay, or in other words, any value that makes your denominator equal 0. All right, so what I want you to do is find the vertical asymptotes for f of x equals x squared minus 36 all over x to the third power minus 2x squared minus 24x. Okay, so a hint, factor the numerator and denominator and simplify it first. And then look at all the values that will make your denominator equal 0. So go ahead and press pause and try to work this one out on your own. All right, so I'm assuming you have pressed pause and worked this one out. So let's go ahead and verify your answer. Okay, so first thing we want to do is factor everything. So you have f of x equals x squared minus 36. That's the difference of squares. So that's x minus 6, x plus 6. And if we factor an x out of each of these terms, we get x times x squared minus 2x minus 24. Okay, and this we can actually factor again. So that's going to equal x minus 6, x plus 6, all over x times, and this factors out to x minus 6 times x plus 4. And we see here the x minus 6 cancels out. So our f of x is equal to x plus 6 over x times x plus 4. Okay, now we go to our second step with, after simplifying, now we find all the values that make our denominator equal 0. Find all values that makes this function undefined. All right, so that means that x times x plus 4 cannot equal 0. Okay, so that means that x can't equal 0, and x plus 4 can't equal 0. Okay, so if we subtract 4 from both sides, we see that x cannot equal negative 4. Okay, so these are your vertical asymptotes. Yeah, pretty straightforward stuff, not too bad. All right, so if you are still writing this, of course, feel free to press pause and finish up. But we're going to go ahead and move on to our next page. Which will look at horizontal asymptotes. Okay, so let our function be a quotient with a polynomial in the numerator and denominator. Okay, everything for your horizontal asymptotes is going to revolve, well, actually just around your lead term. Okay, and you're going to pay attention mostly to your leading exponents. Okay, now there are three possibilities. The exponent up top is going to be bigger than the one on the bottom. The one up top is going to be smaller than the one on the bottom, or they're going to be equal. Okay, so each one of those scenarios has a different outcome. Okay, so if the lead exponent up top is smaller than the lead exponent on the bottom, then the x-axis is your horizontal asymptote. If those two exponents are equal, then y equals your lead coefficient of your numerator divided by the lead coefficient of your denominator is your horizontal asymptote. And if the top exponent is larger than the bottom exponent, then there is no horizontal asymptote, and we will actually look into that a little bit later. Okay, so in other words, to find your horizontal asymptote, just compare your lead exponents. Okay, so visually, this is what a horizontal asymptote could look like. It's basically just a horizontal line that your graph will not cross. That's it. So it will go either this way, or it'll come from the top and go this way, or it can go just one direction. It just will not cross whatever that asymptote is. Okay, and that is what we are going to find. All right, so if you are still writing this, of course, feel free to press pause and finish up, but we're going to go ahead and move on to a couple of examples. All right, so using all the information on the previous page, I want you to find the horizontal asymptotes for f of x equals 2x minus 9 over 3x squared plus 1, for 2x squared plus x plus 7 divided by 3x squared plus 1, and for 2x to the third plus 2x squared plus 3 divided by 3x squared plus 1. Okay, so I want you to go ahead and press pause and solve this one on your own. All right, so I'm assuming you have pressed pause and worked this out. So let's go ahead and verify your answer. Okay, so for f of x equals 2x minus 9 over 3x squared plus 1, when there is no exponent, x is just x to the first power. Okay, so we're just going to look at this first term. Okay, this is your n, this is your m. So we see here that n is less than m. Remember, this is your n, and this 2 is your m. Okay, so since the lead exponent in the numerator is smaller than the lead exponent in the denominator, that means the x-axis equals the horizontal asymptote. Okay, and that's all it is to it. Okay, so let's look at problem B. Okay, so for g of x equals 2x squared plus x plus 7 divided by 3x squared plus 1, we're just going to look at the lead coefficient, or lead term. Okay, so we can see here that this n is equal to 2 and that m is equal to 2. So in this case, n is equal to m. Okay, so since n and m, or n equals 2, let me clear that up. Since n equals 2 and m equals 2, well, let's not even say value, the line y equals, now you're going to use your lead coefficients. Okay, so whenever those two are equal, the lead coefficients are your, well, those would be your horizontal asymptote. 2/3 equals your horizontal asymptote. Okay, so we see here when the top lead exponent is smaller than the bottom, your x-axis is your horizontal asymptote. You see here when they're equal, y equals your top coefficient and your bottom coefficient is your horizontal asymptote. Now let's look at C. You have h of x equals 2x to the third plus 2x squared plus 3 divided by 3x squared plus 1. Okay, so looking at our lead term, we see that n equals 3 and m is equal to 2. So that means that n is greater than m. Okay, so that means there is no horizontal asymptote. Okay, so it's pretty straightforward stuff and really, really helpful for answering certain questions. All right, so if you are still writing, feel free to press pause and finish up. We're going to go ahead and move on to our next page, where we're going to show that when there is no horizontal asymptote, we can actually find your slant asymptote. Okay, so to find your slant asymptote of a rational function, just divide the polynomials and ignore the remainder. Okay, so for f of x equals x squared plus 2x plus 3 divided by x minus 1, find the slant asymptote using this approach. Okay, remember, hint, use long division of polynomials and ignore the remainder. So I want you to go ahead and press pause and try this one on your own. All right, so I'm assuming you have pressed pause and already worked this one out. So let's go ahead and verify your answer. So you have x squared plus 2x plus 3 divided by x minus 1. So we're going to use long division. We could use synthetic division, but need the long division practice. Okay, so we want to get rid of this x squared. So what times x will give us x squared? Well, x times x. Okay, so now we go ahead and multiply. X times x is x squared. X times negative 1 is negative x. Now we subtract. X squared, remember that's distributed, so it's become minus x squared. X squared minus x squared is 0, so that disappears. 2x, remember this distributed, so this becomes plus x. So 2x plus x is 3x. And then we bring down the plus 3. Okay, so now we want to get rid of the 3x. What times x will give us 3x? Well, positive 3. 3 times x is 3x. 3 times negative 1 is negative 3. Now we subtract. 3x minus 3x is 0, so that disappears. 3 plus 3, because remember that minus is distributed, is positive 6. Okay, so we know that x squared plus 2x plus 3 divided by x minus 1 is equal to x plus 3 plus 6 over x minus 1. Okay, but our remainder we ignore. Okay, so y equals x plus 3 is your, not horizontal, slant asymptote. Oh, move that up a little bit. Okay, so it's pretty straightforward stuff. Like I said, not too bad, but everything in a rational function has meaning, especially in your lead terms, in your numerator and denominator. All right, so hopefully this made sense, and I will see you on the next video.